Hi guys, Sauce here. This is a pre-calculus lesson thinking about infinite limits. Let's start with a function we'll define as, call it a. A is equal to 1,000 divided by x. So if we're going to think about this function as an infinite limit, I could write the limit statement, the limit as x approaches infinity of 1,000 over x. How do I think about this? Well, it could help us to think about if x is getting very large, what happens conceptually to 1,000 if it's being divided by a very large number? What is that approach? Well, in real life, we could imagine an object like a pencil, and we divide it into pieces. Each piece, after we divide, is going to be smaller than the original. And if we divide it into more pieces, the smaller each individual piece is going to get. So even if we have 1,000 of something, if we divide it a whole lot by a very large number, the size of each piece is going to become very small. Let's exaggerate this, or literally take it to the limit. If x is getting arbitrarily large, and we could use notation, circle x, which is just a piece of this function. If it itself is going to infinity, what about the whole expression, 1,000 over x? It is going to go to, and eventually then the limit will be equal to 0. Something divided into an infinite number by a large number, or divided into an infinite number of pieces, will have each piece being so small that the size will approach 0. That's the answer to this limit. Notice that this expression, 1,000 divided by x, is very similar to an expression used in one of the limit laws that we've studied. The limit as x approaches infinity of 1 over x is equal to 0. This is a limit law. It's been included in math to help us prove and justify limits formally, as we are beginning to learn how to do. Notice that the function in this limit law and the limit statement is very similar to the function that we used in this example. And they have the same limit of 0 for the same reason. Let's take a look at another function. We'll call it b. b of x is equal to x cubed minus 10,000 x squared. Now, if we're going to analyze this as an infinite limit, we could write the limit statement, the limit as x approaches infinity of this function, x cubed minus 10,000 x squared. How are we going to think of this? Well, let's analyze each term. We have two of them. This term by itself approaches infinity. If x is getting arbitrarily large, then cubing a large number will make it even larger. And notice the way that I wrote the approach of this term. I used an arrow not to mean look for the answer over here. This arrow is notation exactly the same as the limit statement. It's an approach arrow. It's notation to say that this is heading towards or going to or approaching infinity. This second term that I'll circle is also approaching infinity. Think about it. If x is getting very large, squaring it is going to make it larger, multiplying by 10,000, even larger. But this term is being subtracted, so it's negative, or you could think of it as the first term minus the second. Okay, what about the limit? This is a question still. It would be natural to assume that the limit is or could be 0. Why? because we have infinity minus infinity. Something minus itself is going to cancel out, leaving 0. The problem here is infinity is a concept. It's not a value. So the magnitude of these infinities are not the same for any given x value. They're both approaching infinity, but they're not exactly the same number at any particular time, so they don't exactly cancel out, leaving 0. The limit, in this case, is not 0. So how do we analyze this further? Well, this is a function, and it's very nice to be able to visualize functions in a graph. We're going to sketch a graph of this function b. We would need some technology possibly to help us out. But even if we use technology, graphing calculators, the graph would be difficult to show up and see its nature because the magnitude of these numbers is going to be so great. The window settings, in order to capture and see the nature of this graph, it's going to be difficult because, though the nature of this graph is like this tick mark here, which is the value of the lowest point, is about negative 10 billion. And a tick mark here, where it crosses the x-axis, is in the thousands. So if you were to put this function into some graphing technology, it would still be difficult to understand the nature of the graph and use it to find the limit. But this is a sketch of this function, and we can see that in this presentation, the limit is infinity. As x increases, the values of these functions, even though they go very low for a while, turn around and go up forever after. The limit of this function is infinity. Okay, a graph is a great visualization, but it's not formal justification. So if we didn't have the graph, how could we understand from this situation, the limit statement, that the limit is going to be infinity? Well, what other limit could it be? It's not going to be 0. The infinities are not exactly the same value, so they're not going to cancel out. This term here is positive infinity. If this term, being negative, were to influence the other, then the answer to this limit statement could be negative infinity. But it's not, it's positive. And what do we mean by this term influencing this? These two terms you can think of as in a competition for which one is going to influence the final limit. And it's the cube that influences the other. We could say that this cube dominates. What do we mean by that? The cube grows more quickly than the square. In this case, this term being a cube dominates the other one because it grows more quickly, and its influence on finding the limit then decides the final outcome. And this term being positive means that the limit is positive infinity. Let's talk a little bit more about this idea of dominance and growth. We have parent functions that we've studied. I'm going to remind you of parent line, log, quadratic, exponential. And each of these we could consider growing as x approaches infinity. And we can make the limit statement of each. It might help us to see a graph of each of these, or remind us what the graph looks like to help us understand the limit. The sketch of parent line is a function that keeps going up. And so as x approaches infinity, the values of the function approach infinity. Log grows very differently than a line. But as x approaches infinity, the values of log keep going up. Even though they grow slowly, the limit of log is infinity. And the limit of a quadratic function is infinity. And an exponential, as x gets arbitrarily large, also goes up, and its limit is also infinity. We have 4 different kinds of functions, and these 4 kinds of functions increase and keep growing. But what about the rate at which they grow? We can compare them, and this is just going to be a description. The growth rate of a parent line or any linear function is constant. And that constant rate of growth, we have a special way of analyzing it. It's the slope of the line. The growth rate of a log is very slow. Look at what a logarithm does. It grows quickly at first, but it slows down and creeps along compared to the other ones. The growth rate of a quadratic function is fast. This is just a descriptive word to compare it to the others. It grows slowly at first, but it speeds up and it grows very fast. An exponential function's growth is very fast compared to the others. And comparing these growth rates is also thinking about which functions dominate others. Of these 4, the log grows the slowest. As x increases, the rate at which the values of log increase slowly compared to the others. The other functions dominate the log. Constant growth is faster than logarithmic growth. Quadratic will dominate a log and a constant function every time. And the function that grows the fastest is exponential. So how does this help us? This idea of which families of functions dominate others. It can help us understand and find limits. This is the last example. The limit as x approaches infinity of a very unusual function. We're going to include 2 terms. We're going to include the term x to the 9,999. That's a power, huge exponential value, and we're going to subtract 1.00001 to the 0.01x. So what is the limit of this function as x goes to infinity or gets arbitrarily large? Well, let's analyze these 2 terms. This function, or this part of the function, will go to infinity. This is a power with an exponent of 9,999. Imagine putting a small number like 2. 2 to a power like that is going to be huge. Let's compare it to this term here, which is exponential. This exponential function will grow because its base, even though it's very small, is greater than 1. So this is a growth rate that's very slow. And we raise it to an exponent that is positive, but it's very small because we're multiplying the input x by 100th. So this is a very small growth rate raised to a very small power. But it's still exponential, and it goes to infinity. And because this term is being subtracted, we're going to put a minus here. It makes it negative. So what's the limit of the entire function? Again, we have the situation like before. We could think, well, the limit could be 0, or this term could influence it, making the limit positive infinity, or this term could influence it and make it negative infinity because we're subtracting that term. How do we decide? In this case, let's use dominance. Even though this is a power with a huge exponent, an exponential function will always dominate a power. This is an exponential function. It doesn't matter if its growth rate is extremely small and its power is diminished by multiplying by 0.01. Eventually, as x gets arbitrarily large, it's going to win the race. It's going to grow faster, eventually, than any power. So the limit, in this case, is decided by that term. This infinity is overwhelmed by the subtraction of this infinity. The subtraction of this infinity then decides the limit in the end. The limit is negative infinity.